Our speaker is Diana Pholo, spoke yesterday. She describes herself as passionate about research, teaching, and data science. She's currently working on getting a PhD while also working as a data scientist at Predictive Insights, while also being a chief inform officer. Please take it away. We're looking forward to your talk.
Good morning again, everybody. I'm back. And today, what I'm going to share is more focused on my research. So as I just said yesterday already, my name is Diana, and I'm a data scientist and a researcher at the Tshwane University of Technology. So we're going to look at my project using tree-based gradient boosting to distinguish between lymphoma and COVID-19. So what is lymphoma? Lymphoma is a type of cancer. It's a type of cancer that affects the lymphocytes. The lymphocytes are your white blood cells, and they are part of your immune system. So they help you fight infections. And when you have lymphoma, normally those blood cells in a normal person, they have a short lifespan of a few minutes up to a few weeks, and then they die. They naturally die. But when they are cancerous, they do not die, and they just keep multiplying and multiplying. And the usual symptoms of someone with lymphoma is enlarged lymph nodes. They have fever, fatigue, they can have shortness of breath, and they can have night sweats. So you can already see that those symptoms are not very specific to lymphoma only. Even someone with tuberculosis can present with the same symptoms, which is a big problem in countries like South Africa because we have a big tuberculosis burden. So in order to try and fight that problem that we have, we tend to just give the people systematically treatment for tuberculosis if they look like they might have it, just to avoid the spread. And since those symptoms are not very specific, they can also be present in a person with lymphoma, with COVID-19, as we saw. So all these symptoms here, enlarged lymph node, fever, especially fever, fatigue, shortness of breath, difficulty breathing, it can show in a person with COVID-19 as well. So here, I'm showing the X-ray, chest X-ray of two patients. One has lymphoma, one has COVID-19. So which one has which? We are not doctors. I mean, I think there's no doctor in this room, but a professional should be able to kind of distinguish based on this. But still, they make a lot of mistakes because, especially in a country like South Africa, people with lymphoma are generally people with HIV as well. And their symptoms do not express themselves like normal lymphoma would. So they get misdiagnosed a lot. They get diagnosed with TB, for example, and with COVID-19 coming in through the mix, they might just get misdiagnosed as COVID-19 for a little while. And the challenge with lymphoma then in this country is that it gets diagnosed late. So a patient with cancer can wait sometimes a decade before being diagnosed with lymphoma, while they're being treated for other things that they don't have. And with the drastic changes, especially during the COVID-19 time, where there was not enough resources that being supplied to other things, people who would have been screened for lymphoma also went under the radar. So there's a potentially higher delay in the diagnosis of lymphoma, and those people need to be caught up as we are now getting out of the pandemic. We need to actually make sure that we catch all these cases of lymphoma so that we reduce the chances of these people actually dying. So the proposed solution, my solution, is a solution that uses medical text to extract a patient's symptoms, a patient's age, and a patient's gender as a start, and use those features, feed them into a machine learning model, and that model can then classify the patient as having COVID-19 or having lymphoma. And that, even though it wouldn't be used in a diagnosis sense properly, it can be used as a screening tool at a clinic, for example, at a primary healthcare center, where the people who show with symptoms that could be lymphoma can just be screened, and the model can return that whether or not this person is likely to have lymphoma, and then they can be referred to the proper care. So here now I'm going to talk about my methodologies. Now we're going to get a little more technical. The data, where did I get the data? As I said, I was working with medical text, so I needed to get a few medical texts of patients with COVID and patients with lymphoma. So what I got was case reports. Case reports is just a document that reports the course of a patient's visit from the moment they arrive at the hospital, what was their history, what treatment did they get, and all that. And a case report is generally an exception. But if you put a lot of them together, at least we can get a few patterns. So that is why I'm using case reports. So where did I get those case reports? I got them, I didn't say it here, from ScienceDirect, ScienceDirect.com. It's a platform online where people publish a lot of research. So with the credentials I have at TUT, I could have access to a lot of case reports for COVID-19 and for lymphoma. And so they have an API, it's ScienceDirect, that allows you to query the website and get some articles back. And I use the URL lib package to do the URL query. And the URL lib.request module is just what I use to make the request, using the ScienceDirect API, sending my API key, and then my query for the case reports that are related to lymphoma would be lymphoma case report. And then I send through my URL request and open the results back. But I want to note that the API has changed a lot lately. So you might have to do it differently, but I think if you get the concept, yeah, you can still do it. Now, the results that ScienceDirect returns to you is a bunch of articles, but it's in a JSON format. So it just gives you the title, URL of the articles that matched your query. Then I used the JSON package using the method JSON.loads to convert my JSON into a Python dictionary. So I took the response, then I have all my results with my list of articles that are now stored in a Python dictionary. And then I could go through the URL of each article and actually get the text of that article. And the text of that article is in an HTML format. So to read the different nodes inside that HTML format, I use the package called Beautiful Soup. So it takes your HTML text or XML text, and it can find different nodes in there. In my case, I had to find the body. Inside the body, then I would look for sections and look for the section that is, check if the section title is case report or case, for example, or presentation, and filter, only keep those sections to create my data set. So here's an example of a case that would be returned there. So I would look for that section we titled case, and then I would just extract the case that is in there. And the cases have different lengths, and sometimes they're too long. I cut them to not be longer than the average. So I looked at the average length of the cases, and those that were too long, I just reduced the length and removed the characters that were at the end. So after I have my data, I wanted to extract the age, the gender, and the symptoms. First, I'm going to start with the symptoms. I extracted those symptoms with an API by Amazon called Amazon Medical Comprehend. So you create your account on Amazon. You get a few free calls at the beginning when you create your account, and you can send in text. It looks at that text and it returns to you what it finds in there in terms of medications, in terms of symptoms, in terms of signs that the patients presented. So I sent every case report through to Amazon Medical Comprehend, and for each one of them, I got a result looking like this. For example, I filtered out everything that is not a sign or a symptom. So everything that was medication or something I left out because that's not what I need. So this is an example of something that it would return. For each patient, it just returns a list of symptoms and signs that the patient, that it found in that text. So now, if a person wrote cough or coughing, it would be seen as two different symptoms. So I had to do something that's called stemming, where you cut down a word to its root. So that if someone writes cough, if someone writes coughing, it wouldn't be seen as two different words. So I used the NLTK stem, the Porter stem. It's one type of stemmer that's inside of NLTK. If you don't know, NLTK is a library that is popular, used for natural language processing. So yeah, I just explained the why, so that the same symptom couldn't be seen as two different symptoms just because it was spelled differently. And that's one actual problem with medical text. It needs a lot of cleaning. The cleaning is a bit different than your average text. People spell differently. There's a lot of abbreviation. So it takes a lot of work. And that's one of the reasons why I decided, instead of starting from scratch, I'd rather go to Amazon Medical Comprehend, because they've already done a lot of the work in terms of being able to extract entities from the medical text. So here's a snippet of the code and how it would look. So I just defined my stemming function here. I sent through words, and then split them, stem each word, and then return the stemmed version. And from those, for each patient, I got a few symptoms. I created a data set, a data frame with pandas, where each column actually represents a symptom. Now you can see there was a few still things that are expressed differently but would mean the same thing. Like 4 kilos in 2 weeks would still mean weight loss. Abdominal distension, abdomen was soft, abdominal pain. So I decided to group together some of the things with manual lists of synonyms, or by using regex, where I would look for if there's a certain pattern in the name of a symptom, and I take all these patterns, all the columns that fit that pattern, and replace them with one. So I talked about regex, so that was another tool that I used. Regex stands for regular expression. It's a sequence of characters that form a search pattern. The syntax of it is generally very weird, so I personally don't even remember it. I just go to Stack Overflow every time I need to do something. And I use that to check if a string contains a certain pattern. And that's also what I use to extract the age, because different texts had the age written differently. So I had to check years old. Like here I check if there's a number or a few digits. Is it one or many? And then here any character, because some people put a dash, some people put a space, and then years, but some people put years and some people put year. So the S is just optional. And then again, I checked if for this syntax at the end, something old. And I looked at this pattern, and then I retrieved the age with everything that fit this pattern was retrieved as the age, and then I just retrieved the number rather than keeping the whole thing. And the same happened with gender. Many things here, I'm only showing a few examples, but there were very various ways. They would say male, they would say man, they would say gentleman, they would say boy, and all that. So here I just tried to find these few words so that we can separate and create our new feature. And now we have a bunch of features. I don't know, I don't remember the exact number, but we had thousands of symptoms. So I had to actually select those that are most important. So I chose to select it based on correlation. Correlation expresses the strength of relationship between two variables. So I chose those that are mostly correlated with my target. My target variable here is whether the person has COVID or the person has lymphoma. So I calculated the correlation for all the columns, and then I kept a list of columns where the correlation with my target was less than what I wanted. So a correlation normally close to 0 is shows a very little correlation. If it goes towards 1, it shows very strong positive correlation, and towards -1, it shows very strong negative correlation. So I chose to keep everything that was very, very strongly correlated. This was just a test with this value, and I would actually, as my work goes, I would try different correlation values to check which feature set actually works best. So now, after I selected my features, it was time to actually implement the models. I chose to do tree-based modeling. So decision trees, to start with, very popular because they are easy to interpret, which is sometimes very important in terms in fields like medicine. You can't just tell people that, oh, I said you have COVID because my model says so. So it's very, even if you're using a black box model, it's sometimes necessary to also have a model that's capable of explaining part of the decision. So decision trees, they are nice because they can easily be interpreted by humans without even knowing how to code and stuff. And by default, it tends to filter out unimportant features. But one downside is that it's prone to overfitting. It learns so much from the training data that it cannot generalize to unseen data. So one solution is to combine a few decision trees into what we call ensemble classifiers, and this way they perform better. So the first ensemble classifier we used is XGBoost, which is a boosting type of ensemble. So in boosting, you have different weak classifiers, like you would have weak decision trees, and each one of them will classify the patient as having COVID or not. And then the decision of the ensemble is going to be the majority decision of all the decision trees. And this classifier is built stage-wise. So that means that each new classifier that you build, each new decision tree is built by trying to improve on the previous one. So if the previous one misclassified a few examples from the training set, then the newer tree, is going to try and focus on classifying those misclassified things correctly. So that's what we mean by saying it's built stage-wise. So it is advantageous because it reduces overfitting, and then it implements other methods to even reduce it more. For example, shrinkage and column sampling, where we're going to only randomly select a few columns to use in each new tree instead of using all of them. So instead of using all my symptoms all the time, when I build a new tree, I select a few randomly that I'm going to use. This way, I'm not going to be too fitted to the data that I got. And then we tried another tree-based method called CatBoost. It was made to inherently deal with categorical variables, so that instead of you actually having to deal with your categorical variables with things like one-hot encoding, it actually inherently just deals with it itself. And it also tries to remove the number of categories. So if you have a categorical variable that has 100 possibilities, it will cut down to the possibilities that are most present. That way, it's also one of the ways that it reduces overfitting. And then we used Light GBM, which is an efficient tree-based boosting method that aims to improve the speed in terms of processing and also the amount of memory that's used by the model. So it grows the decision tree leaf-wise rather than depth-wise. That means that every time it splits, it focuses on which feature is most likely to reduce the loss. Instead of going by which one is closer to the root, it just goes by which one is gonna leads to a better performance instead. So here I'm just showing a snippet of how easy it is to implement these in Python. You just install your different libraries for the different for those 3 classifiers, and then you can just import the classifiers easily. And I implemented all these classifiers and I evaluated them using ROC curve. The ROC curve is something that shows you how a model is good in terms of balancing the true positive rate and the false positive rate. So in easier terms, it shows you how good the model is at discriminating between 2 classes. Since our goal here is to discriminate between COVID-19 and lymphoma, ROC curve was a good measure, a good metric to measure that. So I don't know why I didn't put the graph there, but yeah, if you can Google, you'll see how the ROC curve graph looks, and a value that's closer to 1 actually means that it's very good at discriminating. A value that's around 0.5 means that your model is as good as a randomly putting people in the different classes. So I did a little bit of tuning. You can see here I used grid search CV. So for each one of the models, because they each have a few parameters that you can set, like when you're going to subsample CatBoost, what is the proportion of columns that you're going to subsample? What is the learning rate going to be? So I don't want to go deep into now explaining what the learning rate and iteration are, but there is a few hyperparameters that you can try. And using grid search CV from sklearn, which is, most people know, a package that allows you to do machine learning, I get grid search CV, and it's going to try for each model, combine all these different hyperparameters. Every combination possible is going to try here. It takes a long time, but I had time, so I just let my computer run overnight and let it try every combination and pick the one that gives the best performance, like so. So here I just call research CV, I send to it my classifiers and my parameters, and the score that I wanted to use in my case was ROC AUC. So you see things are here. I'm just taking snippets of my code. So some things are printed here, but are not defined because they're just defined earlier in the code, and I didn't want to burden you with all that. So what results did we get? So we got 180 COVID-19 cases and 505 lymphoma case reports from ScienceDirect. And this was the gender distribution. And in some of the cases, it wasn't mentioned at all. So most of the patients in both diseases were male, and there was a similar male to female ratio for both of them. And the patient's age varied between 0 and 100, but the COVID-19 patient's average age was a little bit lower on average than the lymphoma patient's age, which actually agrees with literature that lymphoma patients, they generally tend to be a bit older. So that's also what was shown in the case reports here. Here is just a little image of the correlation. I plotted the 10 most correlated features or symptoms. So we had a positive correlation here. Age was mostly positively correlated, and then cough was most negatively correlated. So that means that if a person had cough, the outcome was most likely to be 0 than 1 in my target class. And 0 is, let me remember, 0 is COVID, 1 is lymphoma. So as age went up, the likelihood of the target being 1 was higher, and if someone had cough in their symptoms or breathing issues, the likelihood of having COVID-19 was bigger. And then here's just some exploratory analysis of what the top symptoms were for each disease. So the most listed symptom for TB patients, oh, I said TB here because I previously worked with TB and lymphoma, sorry. So here is lymphoma. It would be weight loss, fever, pain, swelling. And for COVID-19, it was mostly fever, breathing issues, cough, fatigue, abdominal pain, diarrhea, and then you can see here taste smell change, which is one of the only symptoms I got. So if someone had this, they were more likely to have COVID-19 than lymphoma. And here now you see the performance in terms of ROC AUC. They all performed around the same, except IgBM was much, much faster. It was much faster than all of them. And it also had, even though it's a very slight increase, it had the best performance. And when you have, when you call cat boost in Python, you can actually get the feature importance. It can return to you after learning from the data what features were most important in making the classification. So whether a person had fever or not was the most important feature. And then the age, whether the age was below the average in the data set or not, whether the person had weight loss or not, whether they had cough, the patient's gender, and yeah, those were the top 10 most important issues here. So in conclusion, this model is not perfect, but it could be a good tool for just screening patients. It's not a diagnosis tool, which a doctor only can make a diagnosis, but it doesn't take much if it's at the clinic and people already write down reports of the patients and what happened. It wouldn't take much to just run those reports through to a model that can flag people who are likely to have lymphoma and send them through for more diagnosis maybe. So the benefits would be to reduce the delay in lymphoma diagnosis and improve the prognosis of lymphoma patients, because as every cancer, lymphoma you have more chance to survive lymphoma if it was diagnosed early. And the few limitations we have is the size of the data set. We could use more case reports. The data imbalance, I didn't deal with it, but it's part of the next steps I'm going to deal with, because we had way more lymphoma cases, but the model still did quite okay, but we're going to deal with the data imbalance. And then we're going to also try a few more hyperparameter combinations to see if that improves the model. And that's my talk. Thank you for coming.
Have a relationship with what you're looking at. And how do you deal with that? Do you go and look at that like after that to say this feature does make sense, to say it's correlated to your class that you're looking at? And yeah, and the other thing it was about
I'm just looking for the correlation image. Where are you? So here. So those features did make sense because we have a lot of dry cough, a lot of cough and breathing issues reported for COVID patients. And here the model shows that there's a correlation. But I wouldn't say it implies a person would have, because I haven't done causality analysis, which is something that I'm actually going to think of looking at, because I didn't do any causality. There is correlation, but I would not say it implies causation. And I haven't gotten to the part where I would I have done the causality analysis. But in here, it does make sense because age goes up as you have more. If your age is upper, you have more chances of having lymphoma. That goes with existing literature. So that, yeah, I will do causality analysis a bit later. And the next, what was the next question? I'm going to talk about the imbalance. Yeah, the imbalance. I am actually, because this is like one step, I was actually impressed that the model wasn't as biased with the classes being that imbalanced. The model still managed to actually be quite good. Remember, I'm not looking at just accuracy. I'm looking at ROC AUC, because accuracy itself wouldn't be that good of a metric in such an imbalanced data set. That's why I looked at ROC AUC, and the ROC AUC showed that there was a good true positive rate, false positive rate balance despite the data imbalance. So that was really great. And I will just have to see how dealing with the data imbalance actually helps improve this performance.
Martha asks, how would you go about externally validating the tool? Would you get domain experts to help in validating the tool model accuracy, or something else?
My laptop was dying, so I just needed to check it.
Okay.
What I would actually need, if it was really possible, it would be like great to have a clinic, a primary healthcare point where where I'm able to have access to reports, anonymized reports like this, like these ones that I got there, and actually implement them. But that's something that I actually don't know how to go about, because the few professionals I've talked with in South Africa, in Pretoria here, are really not open to the idea of sharing data, because they are very worried about the patient's privacy. So it would be a great idea to actually be able to test it in a clinical setting, but I don't know if that's ever going to happen.
Thank you so much for the great talk. My question is around your results. So the ROC has 89% or 0.89. So I'm asking if you are looking into improving that, because this study is more of a medical issue, and I believe getting as close as possible to one would be like a great idea, so that you make false positives and be looking into improving the ROC.
Yes, I am definitely looking into improving the ROC, but at the same time, I feel like it is important to know that this is the medical field and this is machine learning. So there is a high level of uncertainty in both fields. There is uncertainty in medicine, there is uncertainty in what do you call it? In machine learning. And what would be the main problem here? If I miss lymphoma patients, I feel like it's gonna be, that's what's happening now. They are missing lymphoma patients. But with this tool, we're gonna miss less. That's what I'm aiming for, to miss less of them. And the model itself is not doing the diagnosis. And there must be a human somewhere to say that the model is suggesting that this person needs help. And if they are wrongly flagged as needing to do lymphoma cases, what's the worst that can happen? That they got tested for lymphoma. That's the worst that can happen here, if they were wrongly said to possibly have lymphoma. So it's not diagnosis that I'm advocating, automatic diagnosis, because I don't even think it's legal in South Africa. I think it's a screening tool that can just help actual professionals to have a second opinion, or potentially flag patients that were going to go under the radar anyway. Make sure that as many of them as possible do not go under the radar. But yes, it is always good to have a better model. But the users also have to know that this is not it's not software engineering where it's a yes or no. It's not binary logic. It's machine learning. There is uncertainty, and it's medicine. So someone must come in and decide what to do.
So I just have a follow-up question.
The correlation you
you
looking at, which is age, and you said the patient with the lymphoma shows that as they're aging, then they do have kind of a problem. But with COVID also, that was the case, right? Because young people were probably maybe catching COVID, but not testing as the old people. So most patients then probably were COVID positive in old people. So just looking at that one particular feature, what makes you think is doing the right thing, as compared to say that was like a COVID patient instead of like a lymphoma?
So the age, if you see, I'm sharing again, the average was only almost 4 units difference. So there was a small difference, but still the lymphoma patients in the group tended to be a little bit older. Even though the COVID patients were older, lymphoma patients were still a little bit older. And age will not be used as a single determinant. It's now used in combination with other things. So even though we see that, yes, as age went up, they were more likely to have lymphoma, the model also looks at age in combination with other important features. It looks at all of them. Does he have this age? Yes, but does he have a cough? But does he have? So it's like it's not just age as a feature. This is just like exploratory analysis. We see that there's a 4-unit average difference between the two groups, which is it's not that much according to me, but still shows that the lymphoma patients were a little bit older compared to the COVID patients.
We have time for one final.
Arthur asks, why XVJ boost? Would a deep learning model also work?
I didn't understand the question. You were breaking up.
We're asking about your choice of methods. Why did you choose the methods you did? Would other methods like deep learning also be applicable?
Yeah, so that's what I talked about a bit in the beginning. I chose personally to not go into deep learning, even though I do a lot of deep learning, because I wanted to be in a place where I understand the model a little better. So if at a later point there is the need to implement, I would implement a deep learning model to check if its performance is better. But that's not the only one I would have, because this is medicine and there needs to be a little bit more transparency, explainability in terms of the model. Why does the model make these decisions? Which deep learning doesn't do well? With deep learning, I would take my text and it just has a layer that's going to learn the features. I don't know what it's learning. I don't know why it's learning that. but it knows what it's seeing there, and then it gives me an answer. I would do that later, but I would not discard a model that has explainability just because of the field that this is for, because it's health. It's better to have a better understanding of why the model is making the decisions that it's making.
Thank you very much for that answer. Thank you very much for an excellent talk.
Thank you very much for an excellent talk.
And let us thank the speaker.
Let us thank the speaker.